Right. All right. That's pretty fuzzy, isn't it? It's marginally better. Maybe it would be better with white paper. Just a second. Thank you for bearing with me. Okay. So, not too bad. Okay. So, in my mind, the idea of a Fourier series is, excuse me, is that it's like a trig identity. So you've seen trig identities before. You know, it could be quite some time ago that you saw them, but you've seen things like this. I think it's this. Do you know, I can't remember what it is. Just a moment. I can never remember this, so I'm just going to rewrite it. So that's a trig identity. It goes that cos 2x is cos x squared minus sine x squared. And then usually what you do is you place one of these two things with a 1 minus the other one squared using the fundamental trig identity. And so what you can do is if you go like this one plus this one, you get okay, which means that you can go 2 of cos x squared. Okay, here it is. I always forget this one. I have to reconstruct it from scratch. This trig identity has taken a function that's a bit weird looking, which is cos squared, and rewritten it in terms of constants and cos. And that's the general idea of what a Fourier series is trying to do. It's trying to take a function and rewrite it in terms of cos and sine. So anything that's actually already made out of coses and sines with powers and random things that you could multiplying stuff together and all of those things can be rewritten in terms of cos and sine already. And that's the idea of a Fourier series. This here is the Fourier cos series of this function here. So the idea of a Fourier series is to try and figure out what these numbers are that go with the various combinations of cos and sine and whatever, without having to do all these trig identities. And also to be able to figure that out using derivatives. And integrals. So I'm going to have to look it up in the notes, the exact way of doing it, but that's the general idea. So in the same way that a Taylor series is trying to write something as a polynomial, and we use the way that derivatives interact with polynomials to figure out what the coefficients are, a Fourier series is trying to write this fabulous trig identity for your function. And a Taylor polynomial can find some sort of weird ass thing that's like got squares and things inside other things and figure out what it is expanded out by using derivatives. Same deal with this. But with the Taylor polynomial, we go, well, not all functions are polynomials, but we're going to try and write them as if they were by using an infinite series. Same deal. Not all functions can be written in terms of cos and sine, but we're going to pretend that they can, but we're just going to need to use infinitely many of them. So that's the general idea of the Fourier series. So if the function isn't, I don't have a word for this, but I'm just going to say trig-ish. If the function's not already trig-ish, then you need infinitely many. All right, so I'm just going to look it up in your notes. So give me a second. I don't have a printed version of your notes, so so there's some weird ass stuff about all of these things, and I'm going to skip all that for the moment, and I'm just going to get to this idea here that you've got one. Zoom in on that. 1 and cos x and cos 2x and cos 3x and so on, and sine 2x and so on, that all of these are what we're trying to write things in terms of. And this is going to be our fabulous trig identity involving the constant and involving some number times the cos of whatever x and some number times the sine of whatever x. Just like for my cos squared, it came out to be a half, which would be the a0, and a half of cos 2x, which is the a2. We're going to figure that out for other things as well. But what we can do is we can do it using integration. So in this, when we did Taylor series, we figured out what the coefficients were using derivatives. And when we do Fourier series, we figure out what the coefficients are using integration instead. And the integration, apparently it's all related to dot products and the stuff that you did in Maths 1B with orthogonal projection. And we're just seeing the functions as vectors this time. But that's not necessarily relevant. I think it's cool that the same idea is being used here, but it's really heavily disguised by the fact that we've got integrals here. So for lots of people, it's just easier to think of it as this fancy calculus process that helps you figure out what these numbers are. Okay. Doopy-doopy-doo. Aha. So then there's this version, which changes it so that your function isn't periodic. Okay, so that's the general idea. And the idea is that any function, as long as you consider it to be periodic, then you can do it like this if you want. And that idea means that if you happen to have a process for solving a differential equation that produces infinitely many sines and coses, then that's going to be a Fourier series. And all you need to do, all in inverted commas, all you need to do is figure out how your function can be written in terms of sines and coses to be able to match things up. And that's what the PDEs separation of errors process is attempting to do. So that's why you got told about this, so that you can find a way of solving differential equations, because this entire course is about the various methods that people have come up with over the last couple of 100 years for solving differential equations. And one of those methods, the Fourier series, turns up along the way. And so they're setting up theory about how those things work so that when the Fourier series turns up, you can just use them. But then, of course, because it's a thing that they've told you about, they want to assess you on it, and because that's how university courses work, unfortunately. Okay. Wow, these notes are full of formulas and not much else. Does your lecturer give worked examples in the lecture? That's for you, someone to answer. I'm just interested to know.
Yeah, he does.
Okay, cool. Like just on the document camera sort of thing, or like
Yeah.
writing on the screen, right? Like with his iPad or something.
Yeah, exactly.
Okay, cool. And so there's been an example somewhere of doing some of these things, has there?
I'd assume so. I can't remember off the top of my head there.
That's all right. Okay.
The examples are mostly, so in the notes, it'll have like labeled examples where the lecturer will solve that example.
Oh, I see.
So, yeah.
So
but they're not actually in the notes.
Right. So there's a thing that says there's an example and there's just no actual example. Like this here, example 94, find the half-age expansion of, and then there's just nothing there because that's something the lecturer would have done in the lecture.
Yeah, exactly.
Yep. Okay, cool. All right, cool. Wow, time is moving fast. Thank you for bearing with me with this. This Maths Learning Centre, there's one advantage of not being part of a school, which is we can help everybody in the whole university, but there's another disadvantage, which is that, I don't know what's going on necessarily over in the School of Maths, so it's nice to get, you guys need to tell me. Okay, so I just want to say one thing. I want to talk about this whole periodic extension thing. Just to give, there was something that really confused me for several years of working at the Maths Learning Centre, and I thought I'd say something that really helped me to understand it. So just as I said before, the idea is you've got some sort of function and it's defined on some zone, and it's usually from 0 to L, like this. And there's some sort of whatever it is, wicked function here that's defined only in this zone. And it's usually because when you're solving differential equations, you're actually only interested in a certain time period or a space period. So it might be that you've got, like in an engineering or like in a civil engineering sense, it might be that you've got some sort of cantilevered, iron bar that's holding something up in a building, and it's only so long. And so you're interested in all the forces and stresses and that sort of thing inside that bar. And so it only exists inside this zone from the beginning to the end of the bar. Or most of the time, the things that you use differential equations for involve time, and you're interested in starting at a certain spot and finishing at a certain spot. Or the classic guitar string thing, the guitar string's a certain length and it's vibrating a certain way, but it only exists in this zone. And so most of the problems you're using, the function doesn't go on forever. The theory of functions are that the function is defined on the entire real line. And the theory of Fourier series are that it only works for periodic functions, functions that completely repeat their pattern over and over and over for the entire real line, which is a problem because my function doesn't go for the whole real line at all. It's like this, and it doesn't repeat itself within this zone. And so that's the issue. But it turns out that's not really a problem at all, because since I only need it to work in here, I can make the rest of this function on the rest of the real line whatever the hell I want. And if I can just say, well, I'm just going to imagine that my function is just a slice of a bigger function so that the theory of Fourier series can work for it. And so what you do is essentially you're saying that your function that you've got, I should have brought my plastic sleeves. You can say, oh, that's okay. I'm just going to say it's periodic and copy it forever in every direction. And then now that it's periodic, I can use a Fourier series. Or can I draw this backwards with dotted as well? Now I can use the theory of Fourier series because it is periodic, and someone might come to you and go, but it's not, it only exists in this zone. So it doesn't matter. I just need to be periodic everywhere so that I can make it work everywhere, and then it'll work in this zone as well. So the nice thing about it is that if you want if you get to choose how to turn this into a periodic function, then that means you can decide to turn it into a periodic function that is even and therefore only uses causes, or you can decide to turn it into a periodic function that is odd and only uses sines. You might not get a choice depending on what situation you're in, but if you do get to choose, then you can do what they call these periodic extensions. And so that was a big idea to me that was freaking me out when I was trying to learn this stuff from the students in the Maths Learning Centre. And it finally made sense to me when I said, you know what, it doesn't really matter. No one cares whether your function is periodic or not, because most of the time you can make it periodic if you want to. So that was an idea that I found helpful. So you get a choice to either just straight up repeat it as it is forever, and that's just an ordinary periodic extension, or you can make an even periodic extension or an odd periodic extension. So your choices are, you can make it even first and then make that block repeat over and over, or you can make it odd first and then make that block repeat over and over. And I'm just going to need to go and get something to make that work. Bear with me, it'll only be 2 minutes. Feel free to talk amongst yourselves. Okay, so if I wanted to make this function an odd periodic function, then what I would do is I would turn that into an odd function. So an odd function, when you rotate it around 0, it becomes, it copies itself. So I would do this, like that. And now this piece of it is odd, because this bit down here is the rotation of this bit here. And then what I would do is I would take that whole thing that I've just drawn and I would copy it. So I'd have this, and then I'd copy that here and here forever, and here and here and here. And so that would produce the odd periodic extension. If I wanted to do an even periodic extension instead, then an even function reflects across the x-axis. So I would do that, like that. And then I would take this entire bit like that and copy that, so that I would repeat it here and then here and then here and forever that way. And that's how you would make an odd periodic extension and an even periodic extension. It used to be that you had to draw these in exams, but I've got not the slightest clue what's happening this year, partly because it's a new course and partly because, well, we're in a brand new world of not necessarily being able to draw during exams at all. So, okay. So how do people feel about that thing?
Yeah, that makes sense.
Okay, cool. So basically what that means is if your function's only defined on a small interval, nobody cares. You can still do the Fourier transform anyway. And this sort of thing is important to mathematicians, to say, oh, just a second, well, you know, this thing only works for these kinds of functions. Can we make it work for the ones that we actually see in real life? And that was the idea. Okay, so there are ways of doing this using integrals, but that's okay. And if you can find an alternative way of writing it as a combination of coses and sines, then that works as well, and you don't have to do the integrals at all. And that's an important thing that comes up in some of the classic assignment questions that used to go with this, the course that existed before this one, where there were certain situations where you already knew the Fourier series and you didn't have to do anything special to find it using integrals. Okay, I'm going to do this PDE with separation of variables thing. This is where it turns up, because I've got about an hour to go, and I think it would be useful. Okay, so one of the things that makes this particular, just a second. One of the things that makes this particular thing really hard, and correct me if I'm wrong, but one of the things that makes this really hard is that it's long, and there's a lot of pieces involved. Yeah, so I don't know if everyone agrees with that, but that's my understanding. If I if you agree with me, you could do a yes tick on your thing if you wanted, but it's just long. There's lots of different pieces involved, and each piece has got its own sort of complications. So the first time that happened to you, well, not the first time, but one of the times that happened to you back when you learned maths earlier in your life was when you did completing the square. There's a lot of different pieces involved, and each piece has a different sort of strategy. That's what's happening here. And so what we need to do, what you guys need to do, but I'm going to do it with you, is to try and figure out how all those pieces fit together and how many there are, so that we can keep track of when we've done each one. So your lecturer has tried to be helpful with that, actually. In the lecture notes, here it is. Oh, yeah, okay. So you look at this. This is the separation of variables section. Is that being shared on your screen? Did I not share that?
No, it's not.
Oh, bloody me. That's such a me thing to do. There it is. This is the separation of variables section. And your lecturer has set up a thing with a vibrating string. And then I'm not going to read it at the moment. I'm just going to scroll through it and say there's step 1. And then step 1 has 1, 2, 3, 4, 5 steps within it. And then step 2, 2A, has some steps. And then we have to solve this thing. And then we have to do this. So that's step 2, which had about 4 things. Oh no, and there's still more. And then step 3 has 1, 2, 3, 4, 5 steps. Oh, and then there's the solution. So it's not easy, right? There's a whole lot of different pieces going on. And it can be extremely intimidating looking at that and going, what the hell? How am I supposed to deal with all of that? And that is normal and valid feelings, and you should be feeling normal if you have that. Everybody feels that because it's complicated. There's a lot going on. But a lot of the time there's a lot less going on than all of that. Oh, sorry. If it's really important, they'll call again, and in that case, that might be one of those emergencies I'm looking for, not looking for. Though I was going to say anything to get out of separation of variables, but this is for you guys, and you need to talk about this. So what I'm going to do is I'm going to try and do an example, and work through some of the intricacies of this, and then I'm going to highlight the different pieces of what we've been doing, so that it's not just a big list in your thing there. There's a whole lot of nitty-gritty in here, and it's a classic thing for people to do in an exam because there's a lot of different features that they can test. Okay, so here's where I'd like to rely on you. I can make one up of my own, but that's dangerous for something that's complicated. Is there a specific one from, say, an assignment or a tute or the lectures that didn't make sense and you'd like me to do again? Because if I take it from one of those places, it's likely to actually work. Otherwise, I'll get it from the textbook.
In homework practice problems 10, there's a couple questions on separation of variables.
Yep.
Do you have access to that document or?
No, I don't, but you could email it to me.
All right. Let me do that real quick.
Okay, that's even better. Just going to check this message while you're doing that.
Yeah.
Right, it was spam. Now my email says something has come.
All right. I just sent it.
Okay, cool. I'll give it a little while to sort itself out. Okay. So separation of variables uses a phrase eigenfunctions, I believe. And so it's borrowing some of its ideas from when you did eigenvalues for matrices. It doesn't feel like that most of the time when you're doing it, but the idea behind it is that you're finding functions that when you do the second derivative, they end up being a multiple of what they were before. Yeah. Come on, email's not coming through yet. Okay, I'm just going to set up for my computer. Let's stop sharing that. Thank you for being so gracious, everybody, with this process. There it is. Just a second. Okay. Let's try that again. So which of these questions, thank you for sending that. Which of these questions were you thinking of? Find the vibrations of a string and phase speed. Okay. Wow, okay, so it's getting you to set up the functions as well? Did this come with solutions as well?
Yes, it does, yeah.
Because it would be very nice to know how the lecturer would like people to answer this question.
Do you want me to send you the solutions as well?
Yep, that'd be really useful.
All right.
So I'm presuming, just while you're doing that, I'm presuming that when it says find the vibrations, it means find a formula for the displacement from the center at each position. So I'm just going to see if I can make sense of this first one, actually. So I'm just going to write that down. Vibrations of a string length L equals 1, phase speed C equals 1, 0 initial velocity and initial displacement x 1 minus x squared. Okay. I'm going to just have a quick look in the notes for some of those phrases. Wave equation. 1D wave equation models the vibration of a guitar string. That sounds like what we're looking at here. Phi is the vertical displacement of the string. C squared is T on P, where T is string tension. Rho is its density. Vibration amplitude is small. Doesn't experience gravitational force. A derivation can be found in Kreisig. Okay. So presumably this is the, we need the 1D wave equation because, or is it a 2D one? 2D.
Sorry, David. In the solutions,
Yeah.
it uses the 1D wave solution.
Okay.
The solution of the 1D wave equation, which is given in the notes. So it just goes straight from that because it was already given in the notes.
Sweet. I'm all good with that. And that look at that. I've just in time. You did it yourself by looking at the solutions, and I did it by looking at the notes, and I was only 1 second behind you. I feel proud of myself. And what this says to all of you is that no. I was saying that was just good timing to confirm that what I had just figured out, that this was the equation I'm supposed to use. So notice all of you that I was able to figure that out by searching in the notes for one of the phrases and reading around up and down to see if I could find what I needed. And I need that equation just here, apparently. That's what the solutions say, is it?
It uses the VXT one, so that's on page 102.
Oh, I need to go even further, eh?
Yeah, so I think it solves that equation.
Right.
And then you get the solution to it.
Oh, so it used just the solution of it.
If you missed it.
104.
No, it's 102, sorry.
Yep. So just here, vibrating, that's the drum.
Yeah, and then above, just at the top of that page. Yeah, that one.
So they went straight to this, did they?
Yeah, the VXT part. And then it solved it.
Wow.
Yeah. So you saw that part.
So they didn't actually do the separation of variables thing. Did you just go straight to this answer?
Yeah, it just went straight to that.
Oh, that's unsatisfying. I mean, it's sort of nice to know that your lecturer thinks that you can do that sort of thing. Okay. So presumably So the expectations of your lecturer, therefore, are there are some specific situations such as vibrating strings and drums and stuff where you're allowed to skip straight to the answer, apparently. Okay, so basically wrote this down to begin with.
Yeah, just said
Straight
from
up.
class.
Right. Okay. And then used some of the information that was there and did some of the integrals, presumably?
Yes, it did just the integrals.
Ah, okay. Right. Did you send that to me as well already? Yes, you did. Let me have a look at that too. From class, it's that. Okay. Coefficients are given by that. Okay, so g of x. How did he know that the g of x was 0? Is that because the g of x is the speed, like the initial velocity? That's a good question. The f of x he's used is this one here. This function here has ended up in this spot here. So then he's done an integration by parts, blah, 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 and then got an answer. And so that's the answer. Oh, that is thoroughly unsatisfying, isn't it? Safe place. What a horrible course. Sorry. I guess most...
Reading the lecture notes in example 98, it's
Yeah.
a similar one, and it says 0 initial velocity, and then he's written in his notes gx equals 0. So I think that's where he's coming from.
Right. Well, that is interesting. Okay. So that's here.
Yeah, and it's written because your v subscript t xo equals g of x. So it's something to do with the velocity at time 0.
Right. Oh, okay. Right. And so those functions came out through the whole process of doing this this bit here. Yep. Okay. Wow. Okay. I get it. I would, right. So just a second. So if we follow this through, saying this is the original equation for how a string vibrates, and then being fixed at both ends, we get some extra bits of information. So the velocity of the string. Okay, yep. So what is that? Is that a V? Yeah. So he's working on this equation specifically here, because that's why he's talked about the f of x and the g of x. And the f of x is the velocity of the string at time 0, which we've been given a formula for in our question, which was this x, 1 minus x squared. And then the derivative of velocity with respect to t at time 0 is that g of t, and it's saying that its initial velocity is 0. No, maybe the vibrations isn't, no, that's not a velocity. Don't worry. Why would you use V when there's velocity involved? So that V, I think, is actually a displacement, not a velocity. It's a vibration. It's a distance from where it would be if it wasn't vibrating. I reckon that's what it is, because otherwise this wouldn't be a velocity. It would be an acceleration. So I think that V is actually for vibration. not velocity. Okay, so I think I've managed to sort out my confusion there with how these letters are behaving. That v is not a velocity, it's a vibration, which I think would be a displacement. And then the v sub t, that's the velocity. It's how quickly the vibration is vibrating. And so that's why that's equal to 0. So when he gets down to this, when he does his solution, that's why he's saying that the g is 0, because that's the derivative of velocity. Okay, so how did the g end up in that spot? It's a good question. Okay, I think I would like to actually do the separation of variables properly for that question. I know that your lecturer thinks that you can skip it all, but I'm feeling a little my wife would use the word bemuzzled. I'm feeling a bit bemuzzled about where all these functions ended up and how they ended up in the places that they ended up. And I will feel better about it if I do the whole process. And then it will also illustrate how the separation of variables works. So bear with me, we'll give it a go. So according to the notes, the one-dimensional wave equation is this. Oh, let me just write that down and then I'll skip to my screen. Okay. Okay, that's the one-dimensional wave equation. D squared, curly d squared v over d squared t is equal to c squared curly d squared v over dx squared. And I think that what we're imagining here is that our string goes from 0 to L, which is 1 in our case for this question. And this is an x-axis here. And the v is sort of vibration. Like that. Okay. And then that means that this c, they've also said, is also 1. And so we can do this thing like this. So we're saying that there is some sort of v which says how quickly, how strongly, how far this is vibrating, and it might be vibrating back and forth this way. It might be vibrating back and forth this way. It doesn't really matter. It's basically saying that at every point on here there is some number which is the vibration. And so originally the vibration is this pattern, x1 minus x squared, which helpfully is 0 both when x is 0 and when x is 1. And so it is attached at the ends, which is useful. That's kind of cool. So I would say that there's all these different bits and pieces going on here that we need to write down. So we've got the differential equation here. Since the c is 1, we get d squared v over dt squared is 1 squared times d squared v over dx squared. And then we also have that the velocity at time 0 and position x, not velocity, damn it, vibration at time 0 and position x is x1 minus x squared. And the speed at time 0 and position x is 0. It's always 0. So this is saying that initial velocity equals 0. That's why we say that. Okay. And then the separation of variables idea goes with trying to separate the x's and the t's. And so what we're going to do is we're going to hope very strongly that this v, this vibration, can be written as a product of a function of just t and a function of just x. So that's the big idea that I like to hold on to because it reminds me what to do. So we suppose this v is a function of just t and a function of just x. I don't know which way round the lecturer uses those with an f and a g. Some lecturers use a capital T to be the function of t, and some lecturers use a capital X to be the function of x. I'm just going to have a quick check at your notes to see what your lecturer does. Of course, they use f of x and g of t, which makes no sense because they're not in alphabetical order, but that's okay. Okay. All right. So that's the idea that this is all based on. It's based on this idea that hopefully you can separate this function v, which is a function of both g and t, into two pieces, one piece that's just a function of x and one piece that's just a function of t. And so what that means is that when I find these derivatives, there'll be some interesting things happening, because then I'm going to check one more thing in the notes. Okay. Because then if I do dv on dx, then this is a function of x, and so that'll get differentiated. But the g counts as a constant because it doesn't have any x's in it. And so being multiplied on, it'll still be there afterwards, but I'll have a derivative there. And then the second derivative, the g is multiplied on and it counts as a constant. And so the f will get differentiated too. But on the other hand, if I start from the beginning again and do the derivative with respect to t, now this f counts as a constant because it doesn't have any t's in it. So all of this flows directly from the this assumption that it's made of two functions. And so then what happens is that when we see what this thing here is, that means that we're able to sub into that. Actually, just move it this way and then I can see it all. We're able to sub this in. So we've got here that the d squared v on dt squared is this thing here, which is f of x times g double dashed of t. And over this side, the d squared v on dx squared is f double dashed of x gt. And it being, if we're very clever, we can rearrange this to separate those variables. So we've actually separated the variables twice. First, we separated them into two different functions that were multiplied together. Now we're going to separate them onto opposite sides of the equal sign. So now if I divide both sides by g and both sides by f, now this side is a function of only t, and this side is a function of only x's. And so if it's, so there's no x's on this side, and this one has no t's. If these are the same function, then whatever function that is isn't allowed to have any x's, and it isn't allowed to have any t's either. And that makes it a constant. And so we end up with g double dash t over g of t is a constant, and it's the same as this constant. Whoop, no dash there. And now we're able to take each half of this separately. Now we have to.
Sorry, David.
Yep.
Do you need the c squared in that equation still?
Well, luckily, our c was 1. So
oh,
the
that's
c squared
right.
was
Yeah.
1. Yeah. But normally, you're right, there is a c squared in here somewhere. And so it's normally attached to whichever side it is. So normally there's a c squared here, right? Our c squared happens to be 1, but there's a c squared here normally, and then you end up with the c squared here, and so it's still here. And you're allowed to move it to the other side to make it a 1 over c squared if that's helpful later on, but it is always there somewhere. But for our case, the c is 1. But good point though, it's important to ask those sorts of questions of what would happen if that number was a different number. And in fact, we should probably just pick a different number so that we can see what happens, but we won't be able to check the answer then. Yeah, so this is a very special case. I call that beware of the toast. So beware of things that have 1s as the multiplier, because that means that you're missing information. So normally when there is a c squared, you have to decide whether it's going to go with the x's or the t's. And there is a decision there, and it's based on this information here usually. So whichever one you do first, you want it to not have the c squared in it. I think I could be wrong about that. I'm just going to have a quick look at the notes, because I only get to do this once a year, and so I forget in the intervening time. Yeah, your lecturer has moved the c over to be part of the g. Like that. And there's a reason that they've done that. It doesn't really matter, I'm sure. Okay. Just looking at the thing. Okay. So the problem is that when you, okay, so far, what have we done so far? So far, we've created these new 2 functions, which we're hoping work. One of them is just x, one of them just t, and that's allowed us to create these 2 equations, one here and one here. And we're going to solve those equations separately. But there is a problem in that these conditions here have not been dealt with in terms of the f's and the g's. And so what we need to do is we need to figure out what the f's and the g's do to these equations before we move on. So just like when you do an integration by substitution, you have to get rid of all the x's and turn them into u's. Same deal. We need to get rid of all the v's and turn them into f's and g's in order to do this process. Same as when you do ordinary substitution. It's just that what we do, instead of substituting the x and the t for something new, we're substituting the function itself for something new. So we need to figure out what these are in terms of f and g as well. Okay. So let me just do that for a second. I think we've also missed some things here, because I think that the vibration should always be 0 at the end, at the 2 ends. So we have some extra information too. I'm just going to add it here. The vibration when x is 0, no matter what t is, should always be 0. And the vibration when x is L, in our case 1, no matter what t is, should also always be 0, because otherwise it's just flicking around at the ends here. And if this really is a string that's held in place, those things will never move. So no matter what the time is, the movement will be 0. Right. So we have to turn all of those conditions here into things that involve just the f and the g and not the v. So when I sub, so v of 0, t being 0, becomes f of 0, g of t is 0, no matter what t is. So if this is 0, no matter what t is, no matter which t I pick, it's always 0. That means the only way that could possibly happen is this, if capital F of 0 was 0. So we get f of L g of t equals 0. And if this is 0, no matter what t is, then the only way this could possibly be 0, no matter what t is, if this g changes, is for this to be 0. Like that. So in our case, F is L is 1. Right. So that's interesting. This capital F function has to be 0 at both ends. And in the other conditions, v of x0 is x1 minus x squared. So that would be that f of x g of 0 is x1 minus x squared. And that doesn't really help. I can't make the same arguments I made here because this argument was made because the answer was 0. And this one, yeah, that's not helpful. But presumably g of 0 is a constant, which we don't currently know. Vt x0 is 0, that's interesting. So that would mean that f, the derivative with respect to t of f of x g of t at the spot where t is 0, that comes out to 0. So if I do this derivative, that f of x is going to be a constant because it doesn't have a t in it. I'll get g dashed and then I'll sub 0 into it. Okay, so this is supposed to be 0 no matter what f of x is. So if g dashed of, so the, if these two things multiply to give 0, it could be that this is 0, or it could be that this is 0, but f of x isn't going to be 0 every time. Otherwise, the string's not vibrating at all. And so I reckon that, therefore, since this is true for all x's, that means that g dashed of 0 is also 0. So what we've managed to do is turn this into this new equation. V is f of x times g of t. And we have that f, that 1 over c squared of g double dash t over g of t is k, which is f double dash x over f of x. And also we have that f of 0 is 0, f of 1 is 0, f of x times g of 0 is x times 1 minus x squared. That's unhelpful. And we have that g dashed of 0 is 0. Okay. And now I can see the reason why the lecturer moved the c away from where the f was. And the reason they did that is because this part of it here only involves f. It involves a second order differential equation. This involves f double dashed and f and a constant. That's a second order differential equation of the function f. And it tells me what the value of f is at certain spots. And so therefore this is a very simple equation, and it's made even simpler by moving the c out the way. Yeah, so I would probably should have done this earlier, because then it would have told me whether to move the c away from the f or keep it with the g's. If the g's had come out to be constants as well, then it wouldn't have made any difference. But it's tradition to do the x first. Okay. So I just want to check where we've gone here. We've created this two new functions, one of x and one of g. And that's allowed us to recreate our differential equation into two separate differential equations. That's where the separation of variables happened. It happened once here when we created the two separate functions that multiplied together, and once here when we created the two separate equations. And then we had to do the conditions as well, and that confirmed to us that yes, we should have moved the c squared out of the way. Okay, would anyone like to ask or say anything at this point before I move further? Feel free in the chat if you don't want to say it aloud.
Could you shift the page just up a little bit to see the top again?
There.
Thank you.
So that's all the stuff with the conditions. Is that what you wanted to see?
Yeah, that's fine. I'll just take note of that. Thank you.
I won't be able to do it till Monday, but I will scan all these notes and send them, and put them on the Maths Learning Centre website for you. But I can't do it till I get back to work on Monday. Yeah. Okay. So we've managed to turn it all into this. This is our new set of equations. There is a very sneaky trick here that f(v) actually isn't going to be a function of f times a function of g. It's going to be a whole lot of those things added together. And that's something that didn't make sense to me for a couple of years of helping students with this. It freaked me out. We've sort of made this assumption, but the thing is that this is only going to give us one option for what v is. And to find out what v really is, we're going to have to add all of these options together. So there's actually going to be several different f's and g's that we're going to multiply together, and then we're going to add them together to get the answer for v in the end. Okay. So that's useful. We're going to keep that. And we're going to solve these two equations separately. So we're going to solve one of them and then use the answers to that to solve the other one. Okay. So we're going to solve this. So I'm going to write, I'm going to write down everything that involves an f all by itself without any g's. So I've got this f double dash x over f of x, and I've also got that f of 0 is 0 and f of 1 is 0. This is called the Sturm-Liouville problem. As far as I'm aware. And it's a classic problem. And it is a problem of second order differential equation with constant coefficients. Because if I rearrange this, I can put the f of x up there, and I'm going to remove the x's because I know everything is in terms of x now. So I'm going to put this up here, and then I'm going to rearrange it, and I can get to here. F double dash minus kf is 0. So this is a second order DE with constant coefficients. And that's something that actually was in Maths 1B, but I'm sure it was repeated in this course. And the way that you normally solve a second order DE with constant coefficients is to use a characteristic equation. The problem is going to happen is that we don't know what K is. And depending on what K is, we're going to get different kinds of solutions. So the characteristic equation will be something like lambda squared minus K equals 0. So lambda squared is K. And when you solve these differential equations with constant coefficients, there were three things that could happen. So the three things were either there were two different real solutions, in which case your solution was involving exponentials, or there were two repeated real solutions, in which case your solution involved exponentials and exponentials times x, or there were two imaginary solutions, in which case your solutions involved cos and sine. Now, based on what the answer is going to come out to on what the solutions say, I reckon it's going to be a cos and a sine, but the working is supposed to go through all of those options and rule out the ones that don't work. And so I've got 3 options, and it'll be depending on what this is. If this is a positive number, then I'll get 2 different real solutions. So k is positive, or k is 0, or k is negative. There's 3 things that are going to happen. So if k is positive, it's tradition to give it a letter, usually mu, I think, as far as I recall. It doesn't really matter. So I hope you don't mind if I just do it my own way. So k is either going to be some number squared. That's how they normally do it, so that you don't have to write square root signs everywhere. And in this one, it'll be minus something squared, and it's tradition to use rho. Okay, well, in this case, we get k equals minus mu and plus mu. And when you get 2 real solutions, your solution is going to be that f is going to be something times e to the minus mu x plus something times e to the mu x. And then what you're supposed to do is you're supposed to figure out what the a and the b are. Now, we don't know what this mu is yet, but that's okay. And so then you're supposed to sub in these conditions to tell you what the a and the b have to be. So f of 0 is a e to the 0, which is 1, plus b e to the 0, which is also 1. And f of 1 is a e to the minus mu plus b e to the mu. And these are both supposed to come out to 0. And the thing is, this and this, the e to the minus mu and the e to the mu, they're just numbers, right? But they can't possibly be the same number if mu isn't 0. And so what we get is 2 linearly independent equations. And the only way that 2 linearly independent equations can have a solution is if both of the answers are 0, because what you'll get is this matrix like this. Like that. And then this matrix is invertible because these 2 rows are linearly independent. And so that means that a and b are both 0 at the same time, which is a problem, because that's telling me that if a and b are both 0, then f is 0 plus 0. F is the 0 function. And we know that f isn't the 0 function, because if this string really is vibrating, then f being 0 would mean that the v is always 0 and it's not vibrating. All the vibrations are 0. That's not helpful. So we don't want that one at all. And the same thing's going to happen with this one as well. So in this one, you get k is 0 or 0. There's only 2 solutions. Not k, crap of all crap. Sorry, guys, that's a lambda. K is mu squared. Lambda squared is mu squared. Lambda is plus or minus mu. Lambda squared is 0. Lambda is 0 or 0. K is minus mu squared. Okay, so in this one, we get f has to be a e to the 0x plus a bx e to the 0x. Because that's how it works. You're supposed to have e to the number x and x e to the number x. And so you get a plus bx. And so when I sub that in, f of 0 is a plus b times 0, which is 0, so the a is 0. F of 1 is a plus b times 1, which is 0, but the a is 0, so the b is 0. And since the a and the b are both 0, we get that f is always 0, and so that's not okay either. So that's how this argument works, okay? Now, I need to warn you that sometimes, for very special cases, you will get a solution here Sometimes you'll get a solution here. Sometimes you'll get a solution in two of them. There'll be one here and here, or there'll be one here and here. That's important to know, that sometimes you get both. So in this one, the lambda will be minus rho squared, and so you'll get plus or minus rho I. And so when you get imaginary solutions, the f comes out to something times cos rho x plus something times sine rho x. And now we're supposed to figure out what happens. So f of 0 will be a times cos of 0, which is 1, plus b times sine of 0, which is 0. So that's just a, which is 0. And so now I'm going to do this trick. So f is actually just b sine rho x, because the a was 0. And we're really running out of space here. And not just space to do things. We're running out of options. We've ruled out so many things. We have one thing left that could possibly not be 0. So we're running out of things that f could be. If this string really is vibrating, we need at least one of these answers for f to not be 0. And so we get this. So f of 1 in our case is b sine of rho times 1. And that's supposed to be 0 as well. Okay, so here's the problem. We need that b to not be 0. Because if the b is 0, then we've got f is 0 plus 0, and so we don't have any solutions that aren't 0. So we need that b to not 0. And so since the b isn't 0, I'm allowed to divide by it. So the sine of rho has to be 0, which means that that rho can only be certain things. Sine is 0 when I do my unit circle here and here, which is at the multiples of pi. So rho has to be some multiple of pi. But importantly, this rho, I choose it to be a positive number because when I do the square root, the plus or minus is going to make it, if it was negative, we just get twice of all the solutions. So I'm going to specifically say that it's n pi, but the n has to be positive. Like that. It's not allowed to be 0 pi because then the function back here would be b times 0 and it'd be 0 again. So we're not allowed to have that solution. And so it has to start at 1. If this had been a cos, then it would have been okay for this n to be a 0 probably. Maybe, probably not, because we would have covered the constant solution back here because cos of 0 is a constant. So that's all right. So that's how we end up with only some solutions. So when we track this back here, we end up with coming back here and that the k actually has to be n pi squared, for n being 1, 2, and 3. And if k is that, then the matching f is actually b sine n pi of x. So what I've done is I've taken this answer for rho and I've put it back into this formula. That's how we get that stuff. So I just want to say that there's a different f for each of these values of n, which means this b isn't always the same b. It'll be a constant, but it doesn't really matter. I'm actually going to ignore the b entirely. We're just going to have any function that works. But this is going to be the nth f, and this is the nth k. So the reason they call this an eigenfunction is because when I do the second derivative, it comes out to be a multiple of what it started with. So when you do eigenvectors with matrices, you do the matrix and the vector comes out to be a multiple of what it started with. And so that's what this function is doing inside this equation. You do the derivative and it comes out to as a multiple of what it started with. And since any multiple of it will do, I'm just going to ignore the multiple. Okay, so that bit there, that was all solving, that was all solving this equation just here, which was just this part of this equation. So in order to find V, we have to solve this part of this equation. Now I know I'm at 10:30. I'm just going to keep going until I finish this. I will have to stop at 11 because that's when my next one starts, but feel free to stay. Before I finish this,
sorry,
ask
I have a
something.
question.
Yep.
Yeah, I have a question. With when we substituted back in P equals n pi, was K not equal to negative?
Oh, it totally was. Well done.
Squared?
Yep.
Yeah.
K was minus rho squared, wasn't it?
Yeah, right. Okay, yeah.
Good move.
So that was no problem.
I am honoured that you trust me enough to interrupt me. So, yes, it was minus rho squared. So, a lot of the time in past exams, the lecturer has done this part for you. So, I mean, in that worked example, not work example, in those practice problems, the lecturer had done this entire thing for you and just gotten to the answer at the end. But just letting you know that sometimes they just do a piece of it and they do this part for you. They just let you know that the solution to this is these. So just make sure you don't do anything that the lecturer has already done for you. Okay, so all of this was dealing with that part of the equations we have. So when we go back to the previous equations, now we have that V is still f of x times g of t. But now we know that there's a whole lot of options for what this f could be. And so now we know that there's going to be a whole lot of options for what the v could be. So the nth choice for v is going to be the nth choice for f times the nth choice for g. And we have that g double dash, we have now that f n is sine n pi x. That's what we've discovered so far for n equals 1, 2, etc. And we also have that g double dash t over g of t. The nth g is going to be the nth k, which is minus n pi squared. Okay, and we still have two conditions that we haven't used yet. The f nx. No, that's going to be interesting there. I'm going to deal with that at the end. So we still have this condition here, which I don't like. Anyway, g of dash 0 is 0, and then this final condition, which I'm just going to leave on a separate thing because I don't like it. I don't think this is fn and gn, because this is actually the entire v of x0 has to be equal to this. So our solution was based on there being all these little bits and pieces that all had the same answer. Our solution was based on G being a product of these things, but actually we've now discovered there's all these different answers for what V could be. And it might be that none of them satisfy this, and the only way to get it to work is for the whole thing to satisfy this. Yeah, that's just what I'm thinking. Okay. So I have a feeling that sometimes this other condition isn't going to be able to be turned into something involving just G. Okay. See, yeah, anyway, it confuses me every time. So now we're here and we've replaced all the bits with what we know now, and we're going to solve this equation. I'm just going to leave the n off if that's okay. So when we rearrange this, the g ends up here, and then the whole thing moves over to here. And well, I'm actually just going to leave it like this. That's now also a second order differential equation with constant coefficients. Even though we don't know what the n is, we know what the options are, and it's still a constant. Okay. And so we can use a characteristic equation for this too. So I pulled a little Swifty. Normally you write it equals 0, but I know that it's going to do that anyway. There aren't any things that don't have a g dash or a g in them. And I know that when I do the characteristic equation, the g double dash is going to come at lambda squared, and the g is going to just become a 1. So I can just leave it like that. And so the lambda is going to be plus or minus n pi I. Because I'll square root the -1, that produces the I, and I'll square root the n pi squared, that produces the n pi. I don't have to do all this stuff that I did over here. This stuff here I did because I didn't know what the k was. And so I had to try all the options for what k could possibly be. But in this second differential equation, I don't need to do any of that because I do know what k is. So I can just solve it exactly as it is. And so since these are complex, that means the solutions are that Gn is going to be something times cos of n pi x. Oh no, this is a function of t, isn't it? Plus something times sine of n pi t. And these are going to be different constants for every n. Now we have got some information. We've got that Gn dashed at 0 has to be 0. So now we can use the conditions. Okay, so what are we going to do with this? Gn dashed is, the derivative of cos is minus sine. And then the n pi is going to come out when I do that because of the chain rule. And then the bn's a constant will still be there. The derivative of sine is cos. And then the n pi will come out of that as well. And this is supposed to be 0 when t is 0. So Gn dashed of 0 is minus n pi a sine of 0 plus n pi bn cos of 0, which is n pi bn, because sine of 0 is 0 and cos of 0 is 1. And that's supposed to be 0, which means all the bn's are 0. Which I feel bad about, I think, because it doesn't seem to match the solution. Just let me have a quick look. Oh yeah, no, that's good because there's a Gn. Okay. So this is the point where your lecturer put a g of x here. I've managed to simplify it a little. It's a little different to what your lecturer would do. This bit's a bit different because it was allowed to refer to just one of the values of g. One of the functions g at one all by itself, because I was able to divide out the f. So I didn't have to worry about the same thing that the lecturer has done there. So this is a little bit different. Okay, so now it looks like the Gn, oh, let me just put my thing back on my screen. now it looks like the Gn is actually just an cos of n pi t. And our final condition, as I said, refers to the entire function v. And so I'm not going to be able to do it just based on the individual n's. I'm going to have to put them back together. So Vn is Fn times Gn, which is An cos, what was Fn? Sine of n pi x cos of n pi t. And therefore V is the sum of all of those. Like that. So I've finally got a pretty good answer for what V is. It's made of a product of sines and coses, which is a weird ask, but that's okay. The question is, what am I going to do now? But I haven't actually used the condition yet. The condition is that V of x0 is supposed to be x times 1 minus x squared. So when I do V of x0, that means subbing in 0 for t, and I get the sum from n equals 1 to infinity of an sine of n pi x, and cos of 0, and cos of 0 is 1. And would you look at that, this is a Fourier sine series. And it's supposed to be equal to 1 minus x squared. So what I need to do is I need to find the Fourier sine series of this function. Now, technically, this function is only defined between 0 and L, which is 1. And so I need to do the sort of an odd periodic extension, but nobody really cares about that. I'm just going to do the Fourier sine series. And so if this thing was already written in terms of sines and coses, it would already be a Fourier series, and I would be able to know exactly which of these ANs exist. But in this case, this is a Fourier series with sine. If I figure out its Fourier series, that'll tell me what the ANs are. And that's why when the lecturer did this, when your lecturer was here at this stage, this Bn, that's why your lecturer is doing this thing here. I'm just going to zoom in on that. The reason your lecturer is doing this is because this is how you figure out a sorry, I'm just here. This is how you figure out a Fourier sine series. Yeah. So I've done something. That's weird. The lecturer's written a cos in this spot, but it's supposed to be a sine. Whoops, that looks like a typo to me. Like they put a cos here, that's supposed to be a sine there. Discovered a typo in the solutions. I'll just stop annotating that. Whoa, let me just delete the annotations. So this calculation that they're doing there is to find what I've called AN in my solution, but they've called BN in theirs. And so to find what that thing is, you're going to have to do the Fourier series calculation that finds the solutions. All right. I'm going to have to stop there because I've got another seminar coming, but I have a few more minutes, and therefore I would like to ask people to say things about how they're feeling about this.
I'm definitely nervous about the 2D versions and the radial versions and all that sort of stuff.
I can't make promises of doing another one of these, but our drop-in center is open, so you can have a chat about that. you can go to the Maths Learning Centre and have a chat about it. But give me the weekend to think about it, because I'm just planning my time over the next thing, and I may be able to do another one, which I'll email out and say, look, let's talk about the other versions of this. How do you feel about that as a plan?
Sounds good.
Okay, so I may not be able to promise that, but I will let you know on Monday when I send out the recording for this one, whether I'll do another one. But otherwise, you can drop into the Maths Learning Centre, and maybe you could talk in your pass session about the other one. Yeah, but look, I'll let you know on Monday what my decision is. But I'll just need to sleep on it, if that's okay. Yeah. So I think some questions that would be useful for somebody to ask the lecturer, excuse me, would be whether he's going to expect you to do all of this stuff, or whether he wants you to do what was in that practice thing where you just skip to the answer. Yeah, excuse me. I just want to go to the notes for a second. So that was the one-dimensional one there. And then there's this 2D one, that has several right. What a weird ass thing. Wow. Okay, so they've separated into something that's involving the x and y and something involving the t. Right. And then you're able to get the thing involving the t is the right. Oh gosh.
And then afterwards there's another one where he does it with a circular lid using radial coordinates.
Okay, but the circular one is technically one-dimensional again, right?
He does it using R and theta.
R and theta, yeah, gotcha. So I have a suspicion that he's not going to want you to necessarily be able to do all of the details that go with this that are in the background here, because like on this bit just here, I can't be sure. So this bit here, for example, there, there's a lot going on there. Yeah, I reckon this is a thing to have a try at another session. I'm getting more and more feeling like I want to give this another go, and continue this another day. I will not guarantee it, but I'm feeling much more strongly that I want to investigate this further, because this course is going to exist in future semesters, and it would be nice for us to figure this out. So give me 1 second to, yeah, okay. I'm actually just going to promise at some point next week, I'm going to do another session like this, okay? I've made the promise now. I will let you know when it is, when I send you the video for this one. So that's my promise. I will try not to overlap with the lecturer's consulting times or the past session. So if anybody knows when those are, you could email me and let me know, so that I can not overlap with them. That'd be really helpful. I'm going to have to stop now and get ready for the next one. Thank you for coming, everyone. Oh, that was there's something in the chat. Oh, you're welcome. And the recording's not going to be ready till next week, but I'll email you all to let you know. Thank you very much for coming. And I do wish you all the best, and don't forget the Virtual Maths Learning Centre is open. If several of you are there at once, then there can be impromptu Zoom sessions with the tutors, with multiple people, okay? So it doesn't all have to be one-on-one. But if you don't see me again, I'm just going to say I wish you all the best for your exam, and that you have clear thinking and are able to manage all the information that you've got all at once. Yeah, thanks for sticking around for the rest of the semester. Yeah, I'll see you again soon.
Sorry, that's just that one.
Thanks, mate.
Thank you.